Hello guys, welcome back to a new video. In this video we'll be solving practice 4B. We have the first question. It says, what is the final temperature when a 3 kilogram gold bar at 99 Celsius? So first of all, we have the mass of the gold. You can denote it as M, or you can just write mg, is 3 kilogram, and the initial temperature of the gold is equal to 99 Celsius. Then it is dropped into a 0.22 kilogram of water at 25 Celsius. So we have the mass of the water, which is equal to 0.22 kilogram. Then we have initial temperature of the water, which is equal to 25 Celsius. Cp of the gold, you can refer to the table of the common substances. We have Cp of the gold, which is equal to 129 joule per kilogram per Celsius. Then you have Cp of water, which is equal to 4,186 joule per kilogram per Celsius. It is asking for what? It is asking for the final temperature. So we should find the final temperature of the mixture of water and gold. So TF is equal to what? Remember in the previous video we said that whenever a substance loses heat, the delta T is going to be T initial minus T final. But if it gains or absorbs heat, it's going to be T final minus T initial. So here we're going to say Q lost by the gold, okay, heat lost by the gold is equal to Q for the water, or heat absorbed by the water. Q is equal to what for gold? This is equal to Cp times mass times change in the temperature of the gold. So this is mm. This is equal to what? This is equal to Cp of water times mass of the water times change in the temperature of the water. As we said, because heat is lost by the gold, so delta T here is going to be T initial minus T final. So Cp times mass of the gold. This M just means metal. You can just write it Mg, it's okay. So, or you can just say this is MA and this one is MB, it doesn't matter. Or this one is M1, this one is M2, it doesn't matter. So this is going to be T initial minus T final. This one is going to be what? Cp times mass of the water times T final minus T initial. Let's plug in our givens. We have Cp of the gold, which is equal to 129 times mass of the gold is equal to 3 times T initial of the gold, which is equal to 99. Then we have T final. We don't need it. We don't have it. We're going to find it. So this one is equal to what? 4,186, which is the Cp of the water, times the mass of the water, which is equal to 0.22 kilogram, times Tf, which is T final. We don't have it, minus T initial of the water, which is equal to 25 Celsius. Multiply this with this one. You get what? You get 38,313. Then minus T final, we have 387 T final. This is equal to what? This is equal to 920.92. Make sure to multiply. Multiply by what? By TF, or you can just write TF. Okay, what I'm doing here is just multiply this number and multiply by this one and this one. Okay, then minus multiply this by this, you get 23,023. Okay, since we are trying to find the final temperature, so these two should be at the same side. So what we will do, just move this one to this side and bring this one to the other side too. So this becomes what? 38,313 plus 23,023, which is equal to 920.92 T final plus 387 T final. Okay, then divide this by this number. Before that, you should add these two together and then add these two together. You have 61,336, which is equal to what? It is equal to 1,307.92 T final. Okay, then you want T final alone, so divide this by 1,307.92. Divide the other side too, so 1,307.92. This cancels. T final will be what? Divide this number and you should get 46.89. Okay, or just round this up, it becomes 47 Celsius. This is the final temperature of the gold and water mixture. Question 2, it says a 0.225 kilogram sample of tin at 97.5 Celsius. So first of all, we have MT, or you can just write MM. I'm going to write MM, which is the mass of the metal, is equal to 0.225 kilogram, which has an initial temperature of what? Of 97.5 Celsius. Okay, is dropped into an 0.115 kilogram of water. So mass of the water is equal to what? Is equal to 0.115 kilogram of water. At initially, so it says initial temperature, so this one becomes T initial, which is equal to 10 Celsius. Okay, if the specific heat capacity of tin, it has given the specific heat capacity of tin, so Cp for tin is equal to what? Is equal to 230. Okay, we also have the Cp for water. I always forget this, so this is water and this is tin. Okay, when you are dealing with specific heat capacity problems, you could always make this one. Write the givens for the first substance and write the givens for the other substance too, so you don't mix them. So Cp of water is equal to 4,186. Okay, of course they both have the unit of joule per kilogram per Celsius. So you have joule per kilogram per Celsius. So this time also, Q lost by the tin, okay, this is for tin, is equal to Q absorbed by the water, or Q gained, okay, by the water. So this one becomes what? Cp times mass of the tin times change in the temperature of the tin, which is equal to Cp of water times mass of the water, sorry, this is MW, times delta T. Okay, so we have again the same thing, the same problem as before, just the givens are different. Because tin is going to lose some heat, so delta T for tin is going to be what? Is going to be T initial, so this going to times T initial minus T final. Okay, so this one also is going to be what? Because it's gaining heat, so this one going T final minus T initial. If you have memorized these 2 points, these 2 notes, then you will be able to solve any question. Cp of the tin is equal to what? It is equal to 230. So you have 230 times mass of the tin is equal to what? Is equal to 0.225. Then times T initial is equal to what? Sorry, I forgot to write this. It says what is the final equilibrium temperature. So it needs what? It needs T final. Again, we are trying to find the final temperature. So T initial of the tin is equal to what? It is equal to 97.5, then minus T final. Okay, Cp for water, we have 4,186 times mass of the water, which is equal to, let's check, mass of the water was equal to 0.115 times T initial for water was equal to 10. So T final minus 10. Make sure to multiply again. What we did in the first question, just repeat it and that's it. Multiply these 2 numbers, multiply this number, and then multiply it by this and this one. So you get 50,045.625 minus 51.75 T final. Okay, the other side too, do the same thing. You should get 481 0.39 T final minus 4,813.9 TF. Again, guys, these two should be on the same side. Why? Because you are trying to find the final temperature. So you can take this one here and take this one there. Okay, so you're going to just swap the places, and that's it. So you get 50,045.620 plus 4,000. Sorry, this is not TF. Yeah, this one is not TF. So you get 4,813.9. This becomes what? This becomes 481.39 T final plus 51.75 T final. Add these two together and add this one together too. So you get 9,859.525. The other side you get what? You get 533.14 T final. Divide this by 533.14 and divide the other side too. 533.14 cancels. T final is going to be what? It is going to be 49 Celsius. This is what? This is the final temperature of the tin and water mixture. It is the same steps as before, just you have different givens, you have different values. Question 3, we have what? What is the final temperature when an 0.032 kilogram of milk, so you have milk here, mass of the milk is equal to what? It is equal to 0.032 kilogram at 11 Celsius. So you know T initial is equal to what? It is equal to 11 Celsius. Is added to, you have the next substance, second substance, which is what? Which is coffee. Okay, this time it's not water, so it's coffee. Mass of the coffee is equal to, it is equal to 0.16 kilogram. T initial for coffee is equal to 91 Celsius. Of coffee at 91 Celsius. Assume the specific heat capacity of the two liquids are the same as water and disregard any energy transfer to the liquids. So Cp is equal to water, and this one is also equal to water, which was equal to initial 4,186. Okay, let's do the solution for this one. So you have Q lost by the milk, of course, because milk is added to the coffee. So Q lost by the milk is equal to Q gained by the coffee. Okay, so this is milk and this is coffee. Write the equation for both of them. So Cp times mass of the milk times delta T, okay, is equal to what? Is equal to Cp times, you can write MC times delta T. Now guys, remember it said Cp of both of these substances is equal to what? Is equal to the water. It means this Cp with this one are equal. So what we are going to do here, if you have the same number on both sides, of course it's going to cancel each other. So this Cp is going to cancel with this one. So you have mm, mass of the milk, times the change in the temperature of the milk, which is equal to mass of the coffee times the change in the temperature of the coffee, of the coffee. So mass of the milk was equal to what? Was equal to 0.16 times 91 minus T final is equal to what? Is equal to 0.032 times, because of course coffee is going to gain heat, so it's going to be T final minus T initial, so T final minus 11. Okay, multiply this by this and then multiply it by this one. You should get 14.56 minus 0.16 T final, which is equal to what? It is equal to 0.032 T final minus 0.352. Okay, take this one to this side and take this one to the other side. You should get 4.912, which is equal to 0.192 T final. I just added the numbers and that's it. And divide this one by 0.192 and this one 0.192. Cancels. T final is going to be equal to what? 78 Celsius. This is the final temperature of the milk and coffee mixture. We have question 4. A cup is made of an experimental material that can hold hot liquids. The 0.75 kilogram cup, so you have the mass of the cup, which is equal to, you can just write MC, which is equal to 0.75 kilogram. Has an initial temperature, so T initial is equal to 36.5 Celsius. When it is submerged in, so we have the second substance, which is water, is equal to, mass of the water is equal to 1.25 kilogram with an initial temperature, so T initial is equal to 20 Celsius. What is the specific heat capacity if the final temperature is 24.4 Celsius? So T final for both is going to be 24.4 Celsius. T final is going to be 24.4 Celsius. We need what? We need the specific heat capacity for the cup. We know of the water is equal to what? 4,186 joule per kilogram per Celsius. Now, Q lost, or the heat lost by the cup is going to be, so this is for the cup, is equal to the heat gained by the water. Okay, again, write the full equation. You have Cp of the cup times its mass times the change in the temperature. This is going to be what? Cp of the water times mass of the water times the change in the temperature of the water. So Cp, we don't have it for the cup. We have the mass of it, which is equal to 0.75. Because, guys, the cup is going to lose heat, so the temperature for it is going to be T initial minus T final. Okay, so T initial is equal to what? It is equal to 36.5 minus 24.4. Then Cp of the water is equal to what? 4,186 times mass of the water, which is equal to what? Is equal to 1.25 times delta T for the water is going to be T final minus T initial. If I ask you why, you should say because it is gaining heat. If it gains heat, the delta T is going to be T final minus T initial. 24.4, which is the final temperature, minus what is the T initial for water, is going to be equal to 20. Okay, multiply all of this, okay, by this one and by this one too. You should get Cp times 9.075, which is equal to what? Is equal to 23,023 Then divide all of this by 9.075. Divide the other side by 9.075. You should get what? Cp is going to be equal to what? It is going to be equal to 2,537. What is the final unit? Don't forget, joule per kilogram per Celsius. This is what? This is the Cp for the cup. Okay, this is the Cp for the cup. This is question 4. Question 5, we have brass is an alloy made from copper and zinc. A 0.59 brass. So we have what? First of all, we have brass here. The mass of it is equal to it. I'm going to write MB is going to be 0.59 kilogram. Sample at 98. So it's what this is T initial. It's going to be 98 Celsius. It's dropped into 2.8 kilogram of water at 5 Celsius. So we have water again. Mass of the water is going to be equal to 2.8 kilogram. T initial for water is going to be 5 Celsius. If the equilibrium temperature is 6.8 Celsius, what is the specific heat capacity of brass? So specific heat capacity is going to be what? If we know T final for both of them is 6.8, and also for the brass is going to be 6.8. Okay, let's solve this again. So again, Q lost by the brass is going to be Q means heat, gained by the water. Write the full equation. You have Cp times mass of the brass times change in the temperature of the brass, which is equal to what? Is equal to Cp of the water times mass of the water times change in the temperature of the water. Again, because brass is going to lose heat, so it's going to be T initial minus T final. Water is going to gain heat, so delta T is going to be T final minus T initial. Cp, we don't have it for the brass, is going to be times what? Times 0.59, which is the mass of the brass, times, we said T initial minus T final. T initial for the brass was 98 minus 6.8, which is the final temperature, is going to be what? Cp for the water is equal to 4,186 times mass of the water, which was equal to 2.8 times the final temperature for the water was 6.8 minus initial temperature was equal to 5. So multiply this one by this one and by this one too. You should get what? You should get Cp times 53.808, which is equal to what? Again, multiply this by this and by this, or you can just subtract this and then multiply it by this one. Again, you can do the same thing for this one too. So you have 210,097.44. Okay, this is point. Divide this by this, 53.808. Divide this by 53.808. Cancels. Cp is going to be equal to what? Cp for the brass is going to be 392.08 joule per kilogram per Celsius. We have question 6. Question 6, it says, the air temperature above coastal areas is profoundly influenced by the large specific heat capacity of water. How large a volume of air can be cooled by 1 Celsius if energy is transferred as heat from the air to the water, thus increasing the temperature of 1 kilogram of water by 1 Celsius. The specific heat capacity of air is approximately 1000 joule kilogram per Celsius, and the density of air is approximately 1.29 kilogram per meter cubed. First of all, we have what? We have delta T, this is water, this is air, and this one is water. So for air, we have what? We need to find the volume, okay? For the air, we should find the volume. So we don't have the mass, okay? But we have something else. We have the specific heat capacity, which is equal to what? Which is equal to 1000, okay? Joule per kilogram per Celsius. And then we have what? We have delta T. Okay, it says what? How large of volume of air can be cooled by 1 Celsius. You don't have initial temperature and initial and final temperature, so this is going to be what? This is going to be delta T, the change in the temperature of the air. And then for the water, we have what? We have 1 Celsius and we have 1 kilogram of water. So mass of the water is going to be 1 kilogram, and delta T of water is going to be what? Is going to be 1 Celsius. So Cp also is going to be what? 4,186 joule per kilogram per Celsius. Okay, now we should do what? We should take Q lost by the air, this is air, is equal to what? Is equal to Q gained by what? By water. Okay, so Cp for the air times mass of the air times delta T of the air is equal to what? Is equal to Cp of the water times mass of the water times change in the temperature of the water. I can just say this is MA, this is MM, so that we don't confuse them. Here, as we said, delta T is going to be 1 Celsius, and for this one is also going to be 1 Celsius. Because in the question, it doesn't say final or initial, so it's going to be what? The change in the temperature of the air and the water. Cp for the air is going to be 1000. Mass of the air, we don't have it, times 1. Then this one is 4,181, which is Cp of the water, times 1 kilogram of water times 1 Celsius. This is going to be what? 4,186 is equal to what? Is equal to 1,000 MA, which is the mass. Then mass of the air is going to be 4,186 divided by 1,000. We have what? We have 4.186 kilogram. This is what? This is the mass of the air. Now, how can I find the volume? Remember, guys, you know the equation for density. Okay, how can I find the volume? Density is equal to what? Is equal to mass over volume. You might say, how do I know I should use this equation? Well, take a look at the question, and it says what? It says density of air is approximately 1.29. So if you find the mass of the air and you have the density, you can find the volume. So the equation for volume will be what? Mass divided by density. Mass is equal to 4.186 kilogram. Then this is equal to density is equal to 1.29 kilogram per meter cube. Kilogram cancels, and you have what? You have 3.25 meter cubed. We have question 7. Question 7, it says what? A hot, just minted copper coin is placed in 101 gram of water to cool. Okay, the water temperature changes by 8.39 Celsius, and the temperature of the coin changes by 68 Celsius. So what is going to be the mass of the coin? Disregard any energy transferred to the water. Again, we're going to do like this. So you have coin, you have water. Okay, what's the mass of the water? It's 101 gram divided by 1000 or multiplied by 10 to the power minus 3. You're going to get 0.101 kilogram. Okay, what is the change in the temperature of the water? Is equal to what? Delta T. Again, you don't have initial, you don't have final, you just have the change in the temperature, so it's going to be what? 8.39 Celsius. Okay, and the temperature change of the coin is equal to what? Is equal to 68. So delta T for the coin is equal to 68. It says what is the mass of the coin? We don't have the mass of the coin, so MC is equal to what? Disregard any change to the surrounding. Cp for the coin is equal to 387. Cp for the water is equal to 4,186. Okay, let's do this. It's really easy. Q lost by the coin is equal to Q gained by the water. Okay, this is water and this is the coin. Write the full equation. You have Cp of the coin times mass of the coin times the temperature change in the coin is equal to what? Cp of the water times mass of the water times the temperature change. Cp of the coin is equal to 387. Do you have the mass? No. So you're going to say times mass times the temperature change in the coin is equal to 68. Then this is equal to what? Cp of the water is equal to 4,186 times mass of the water is equal to what was the mass? Sorry. 0.101 times the temperature change in the water, which is equal to 8.39. 8.39. Let's reach again 8.39. Now multiply all these numbers. From this side you get 3,547.17, which is equal to what? Is equal to 26,316 mc, which is the mass of the copper. Divide this by this number, 26 times 316, and this one too, 26,316. Cancels. Mass of the copper is going to be equal to 0.1347 times 10 to the power of 3, or basically 135 gram. We have question 8. It says the temperature of water at the highest point of Niagara Falls is 10 Celsius. So we have temperature of the water, which is equal to 10 Celsius, which is T initial. Assume that all potential energy of water is transformed into internal energy, and that each 4,186 joule kilogram per Celsius leads to 1 Celsius increase in the temperature of the water. We don't need that information, this one, a 1 Celsius increase in temperature of the water. If 505 kilogram of water falls a distance of 50 meter, so we have the mass of the water, which is equal to 505 kilogram. What is the height? Height is equal to 50 meter. What would be the temperature of the water at the bottom of the fall? So we had T initial, it is asking for T final. Okay, now here you don't have two substances, you have only one substance, which is water. Okay, if you want to find T final, okay, you only have one equation, which is equal to delta T, T final minus T initial. Okay, take this one here, and delta T plus T initial is going to be what? Is going to be T final. Okay, do I have the change in the temperature of the water? No, I only know the initial temperature of the water. So I'm going to first find this one, put it here, and then find delta T. Let's do this here. This is really important because it says assume that all potential energy of the water is transformed into internal energy. This means that Q, which is heat, of course it's energy, is equal to PE, okay, which is potential energy. Then P is equal to what? PE is equal to mgh. PE is then going to be 505 kilogram, which is the mass of the water, times gravity 9.81 times the height of the fall. Okay, P is going to be what? Is going to be 247,702.5 joule. This is the potential energy. Okay, here we said that heat is equal to potential energy. Why? Because all the potential energy is transforming into internal energy. So what we are going to do here, we're going to say Q is equal to mass of the, or we can say Cp of the water times its mass times the change in its temperature. So using all this information, we're going to find delta T. Here, careful, we said that Q is equal to what? Is equal to PE, and we already found PE, which is equal to 247,702.5. So we're going to say what here? We're going to say 247,702.5 is equal to CB of the water, which is 4,186, times mass of the water, which is equal to 500, times delta T, which we don't have it. Divide all of this by this, 4,186 times 505, cancels, divide this side too, 4,186 times 505, then delta T is going to be what? It is going to be 1186 Celsius. This is what, guys, this is the change in the temperature of the water. Is that it? No. Remember here, we said to find T final, we're going to say delta T plus T initial. We found delta T, which was equal to 0.1186, okay, plus T initial was equal to what? Was equal to 10, okay. T final is going to be equal to 10 point, you can just say 1 or just 10 Celsius, it's enough, okay. This is the final temperature of the water at the bottom of the fall. This is it, guys, for today. See you in the next video. If you have any questions, please comment below. See you in the next video.